Oke, assalamualaikum warahmatullahi wabarakatuh. Oke, jadi my primary present our discussion is introduction by Coffee. Which is the topic that we will present is Euler equations of motion of the rigid body. So, let me introduce how our body works. The first one is coordinate and magnetism. The second one is unilateral spin of the organ. The third one is self-down mechanism. And the last one, non-circular gravity. Okay, so the content that we will present for you today is the three content, which is the introduction, application, and the last one is the question. So, let me pass to Anis for the concept of equation.
Okay, so Assalamualaikum, I am Anis here and I will be presenting on the concept of Euler's equation and the application of law. So for the concept of Euler's equation, it is an equation that basically describes the rotational motion of a rigid body on each of the principal axes. So when an object, say, let me explain what is a rigid body first. A rigid body can be considered as any object that when you apply force onto it, it doesn't change shape or the change on the body itself is negligible. And so when a rigid body is rotating, whether it is on any of the principal axes, whether it's x, y, or z from the inertial frame of reference, the rigid body itself has its own rotational frame of reference that is centered on its center of mass. So when an object rotates on any axis, the position of the axis itself in the object, the rotational frame of reference, will also change based on that rotation. Next. Okay, so this is the equation, and we obtain the equation based on the angular momentum equation, which is then derived to a derivative of angular momentum with respect to time, where n is the applied force. And using the derivative for rotating frame function, you can see it is dl over dt inertial, which is let's say our frame of reference. We have to change it to the following equation, where it is L over dt rotating plus omega times cross product of L. And we also then we have to take note of our equation is L over dt equals to L dot equals to I omega dot. And the omega cross product of L equals to omega times omega cross product I dot omega, which is converted into a cross product determinant. The first product of the fourth step and the second and the cross product determinant is then substituted into the third equation, which forms into an equation in a matrix form, which is Euler's equation in body motion. Next. So as for the law, I want to ask, it's more like so when you can see the picture that this object is called gyroscope, it is spinning, but when it is spinning, you expect that it would fall, but instead it is stayed upright. The behavior, it is a phenomenon called gyroscopic precession, which is something that can be explained using equation. But since I don't have a gyroscope, I just have to do with this coin. When you, let's say for example, right, when you spin the coin, when you spin the coin, right, it stays upright until it stops spinning. Basically, it is that the gyroscopic precession is when an object, a rigid body, is spinning. It generates torque, and that torque is also followed by angular momentum. That angular momentum wants to follow the torque, but since it's constantly spinning until it doesn't, the angular momentum can't keep up. So it is what keeps it upright. The torque is usually, let's say, but in this case with the spinning coin, it is produced by the gravitational force and the normal force that's acted from let's say, from the coin stick on the table itself. So that's all for me. Next, I'll pass it on.
Okay, next I will present about the concept in the fidget spinners. Fidget spinners are basically a little gyroscopic, bringing in these very physical properties, and we can learn many concepts through playing with the spinning toys as well. For example, by examining and studying fidget spinners, we can understand many concepts physics in this object, such as gyroscopic motion, friction, and also inertia. Pocket gyroscopic are exactly what fidget spinners are. Gyroscopic are rotating objects fixed on an axis that stabilize a body by preventing from moving due to rotational momentum. This idea is easy to understand when using a fidget spinner. The fidget spinner itself will resist any attempt to rotate it in a direction that is not a parallel to its axis of rotation. When you play with a fidget spinner, another thing that happens it often differently from how you would anticipate. Okay, next. Next. Okay, this is the application gyroscopic, the illustration in the fidget spinners. As the wheel spins at a rate Ws, the gyroscopic precesses at a rate Wt about the pivot at the base with the constants. When we take a closer look at this, we are left with the gyroscopic precision concepts. Take a fidget spinner. Gosh. And try to twist it forward to observe this in action. The spinner sorts of ties at a diagonal angle to the spinner direction, as opposed to tilting forwards as you would prefer. Just like in the figure, gyroscopic precision is the primary process of this diagonal rotation. When a force is applied to a spinning body, a force that travels in the direction of rotation 90 degrees after the point of impact is known as a precision, as known as a gyroscopic precision. Next, we go to the next application in daily life.
Okay, thank you, Firdaus. Okay, the next application of Euler equation of motion of a rigid body is where we can see it in the spinning top, where the spinning top is the type of toy that designed to spin on its vertical axis. and it balancing on the tip due to the gyroscopic effect. Okay, for a spinning top, the gravitational pull act downward from the center, and the force of equal magnitude act upward from the tip, like touching the surface that the top is spinning on. Thus, a pair of equal and nearly opposite force is formed, which keeps the top spinning. As we can see, this is the equation, and the position and velocity of a spinning top is inversely proportional to its spin speed, where when the spinning top try to balance, which is you can see in this video, like that, we can see it will not straight up, but there will be like an invisible axis to fall down, like when it stops it will fall down, right? Okay, and it has like the same concept like the gyroscopic, like in this video. Where it try to stabilize it rotation. Okay, I will pass to the next person.
Question, which is that the thin uniform rod of length J and mass is constrained to rotate with constant velocity about an axis passing through the center of the rod and making an angle alpha with the first question is show that the angular momentum L about O is perpendicular to the rod and all is of magnitude. And the second question, example is using the Euler equation to prove that the top vector n is perpendicular to the rod and to angular momentum and with magnitude. Okay, so for the first question, we know that using the Euler equation, moment of inertia of the rotating rod of axis I1 is equal to ml square over 12, and also the I2, but different with I3 because it is perpendicular to the rod. Okay, now we solve the component of the angular velocity. We know that the of angular velocity is omega E1 sine alpha plus E is cos alpha. Write the relation for the momentum about each and perpendicular to the rod. This is L I, which is ml square over omega, and times omega E1 sine alpha plus 0 plus 0. And then we get the last equation, which is we can prove that we can show that the magnitude is equal to ml square omega over plus sine alpha. And the next question is the Euler equation. Prove that the top vector n is perpendicular to the rod and momentum at the magnitude. It mentioned that omega is constant, so since omega is constant, n1 is equal to 0, while n2 is equal to the formula of the function O plus 0 plus omega sin alpha times with omega cos alpha times with square omega. 3 is medium. Therefore, the vector n perpendicular to the road is n vector is time with n square to the class square sudah sin alpha cos alpha. That's how formulate can get the n vector is square omega square sin alpha. Okay, next. So for example, this particular kind of integration explain how to utilize it to derive the equation for the overall motion of the rigid body. This equation for this chapter.
So, is there any question for the audience with us? Okay, Nurhani's people.
Sorry, but can you explain again about gyroscopic in fidget spinner? Because I'm a bit confused about it.
Okay. Actually, many applications that can be applied in daily life with the in gyroscopic position. But I choose the fidget spinner. Fidget spinner are basically a little gyroscopic in this physical principle. So we can learn many concepts from these fidget spinners. By examining and studying fidget spinners, we can understand exponential, decay, and also gyroscopic motion, friction, and inertia. Okay, gyroscopic are exactly what fidget spinners are. Gyroscopic are rotating object fixed on an axis that stabilize a body by preventing it from moving due to the rotational momentum. This idea is easy to understand when using a fidget spinner because it will resist any attempt to rotate it in a direction that is not parallel to its axis of rotation. For the example, when you play with a fidget spinner, another thing that happen, it often move differently from how you would anticipate to the fidget spinner. Okay.
So, any other audience want to ask question? If there is no other question, so that's the end of our group presentation. So thank you for joining our presentation.